we went through and just kind of looked at the data and looked for simple comparisons. So for instance, we compared experiment 1 to 2. And we looked all the way through at those, and we said that in the course of that experiment, we noticed that the nitrite concentration stayed the same, so that's not going to have an effect on the rate, because if it doesn't change, it can't change the rate. Okay? And then we looked at the ammonium concentration and noticed that it doubled. Okay? So if we double the concentration of the ammonium, that could potentially change the rate. So we now go back and look at the rate and see how it changed. And we look at the rate, what happened? It also doubled. So what we're doing is actually the same thing that we're doing, or that we ended yesterday with, except yesterday we went through and showed all the mathematics behind it. Instead of looking at strict just one-for-one comparisons that are a lot easier for us to do kind of mentally, we looked at the mathematics behind it. How did we actually solve that? Okay? So let's take a closer look mathematically at what we did. To determine it doubled, what did you do? What did you do inside your head when we look at the concentration of ammonium? First off, can you all agree? Did it double? Yes. How do you know that? What did you do to determine that it doubled? So what we did is we took the experiment, let's make sure I'm in the right set. We took our concentration of ammonium in experiment 2, and we divided it by the concentration of ammonium in experiment 1. Okay? And we said that that was proportional. We'll actually say it's technically equivalent in a second. Proportional to what? What did we compare our concentration to? The rate. What did we decide happened with our rate here? How did you know it doubled? What did you mathematically do? You took the rate of experiment 2 and you divided by the rate of experiment 1. And you saw that it doubled. Okay? When we go through and do this mathematically, we notice you got the proportional sign in there. Okay? There's an extra term that technically has to show up in this. And when you go back and look at what we wrote up at the end of last lecture, and I've got it typed up so it's a little bit easier to see here in a second, we added an extra piece. That extra piece was our nitrite concentration. To make that an equivalency, to get rid of the proportionality, we have to then add our nitrite concentration to this. So we could go through and say our nitrite for experiment 2 over our nitrite for experiment 1. Now we can say those are equal to each other. We can get rid of the proportionality, and we can say they're equal. Why, when we did this in our heads, sort of in our heads, did we not look at the nitrite? Why did that term not show up mathematically? Because it canceled out. Okay? So these simple kind of just looking at the data to try and come up with these comparisons, it's something that you can do fairly readily within your head, and you don't realize that you're actually going through and solving it strictly as we went through and did it yesterday. So yesterday may have looked really confusing. Was it confusing? Only 2 people, really? Everybody else thought it was easy? Okay, I'm sorry. So that's where it's coming from. Okay? We could then go through, and what did we do for the, and ultimately what this gave us was that x. Because 2 to the x equals 2. What does x have to be? 1. So again, what you're doing is solving for it in your head. That's one of the trivial cases. It's a little bit easier to see. Yes?
What does that x mean?
We'll talk about that in a second, too. That's actually where I wanted to go yesterday before solving, and I forgot. Okay? So that x is mathematically necessary for the relationship between these two. Okay? So these x and y's allow for this equation to be true. So that's its mathematics. We haven't discussed what they physically mean as far as the experiment goes or as far as the chemistry goes. Okay? So we'll look at that in just a little bit. Okay? We could then go through and solve for the y value. How did we solve for the y value? That y value is looking at how the nitrite concentration is dependent on the rate. So we then went through and picked another sequence of experiments. Which ones did we pick? I think we picked 5 and 6. And when we look at 5 and 6, we did a very similar situation. We went through and determined that our nitrite concentration doubled as we went through 6 to 5. How did we figure that out? We took the nitrite concentration of experiment 6 and divided it by the nitrite concentration of experiment 1. Got 2. Okay? We then also went through and compared it with our rate. Very similar setup as we had set up here. Okay? And technically we've got our y in there. Bit tight. Okay? And now in this new sequence of experiments, what happens to our ammonium concentration? Stays the same. So what happens to that term in this equation? Again, drops out. We don't have to worry about it. Okay? So what we were able to do within our heads was ultimately set up a relatively complex equation, and we just kind of ignored certain terms and dealt with the simple numbers, or hopefully easier numbers to see. Yes?
Once you find out, say x and rate, you just simplify it because when you divide that for the first one, you end up with 2, right? And the rate is 2 as well.
Yes.
So then, but then you have xy equals 1, so you just simplifying, you know what I'm saying?
So what we end up solving for, so in our first case, in our black boxed in case, we said the nitrite concentration didn't change, which means this term drops out. This term is still here. We still have a rate here. When we go through and solve that, I don't have any space. We would get, let's see, let me match the colors again. We would get 2x equals 2. We could now solve for x, and we would know, if I kind of cover up the y there, we would know x equals 1. We could make that x equal to 1. We then go through and do it again for y, and that's now our red case. And we go through and set up our red case where we compare experiment 6 to 5. We end up with the same ultimate equation, except now instead of it being 2x, it becomes, whoops, that should be red. It becomes 2y equals to 2. So what does that mean y equals? 1. Okay? Now that we've got that information, we shuttle that back into our equation, and we now know what x and y are. Once we know what x and y are, what can we solve for now? Now we can solve for the rate constant. This was something that originally I had intended for you guys to go through and solve on your own and verify that all of the rate constants came out the same. Okay? Since I didn't show the answers, I figured I'd go ahead and calculate them and show you now. So when we look at each of those individual experiments, the concentrations change, the rate changes. And yet, if I go through and rearrange my equation and solve, whoops, let's do this one, and solve for k, I get k equals the rate over NH4 plus to what power? 1. How do you know it's 1? Just solved for it by doing our comparisons to our data. Times our nitrite concentration to what power? 1. We can now solve for k. And if we go through for each individual experiment, we have to make sure we don't swap data. It's one of the easiest mistakes, particularly when you have so much data. If I want to solve for the rate constant in experiment 1, I'm going to use the rate for experiment 1, and I'm going to use the ammonium concentration for experiment 1 and the nitrate for experiment 1. Okay? When you've got so much data there, I know you're all going to go, okay, yeah, it's really easy. I would never make that mistake. Particularly on an exam, if you've got so much data to weed through, it may be easy to really number swap and slide something else in there, which is why it's important to show your work when you go through and do these things. Because if you get an answer that doesn't make sense, you can quickly go back and say, that number doesn't match experiment 1. Okay? If we go through and solve it for experiment 3, we now change all of our rates and concentrations, and we get another rate constant value. What's the difference between those two numbers? Really, really small. How about the next one? Did I do this right? Yeah, I did. fact, the rate constant for each of those is relatively the same. Why is it not exactly the same? What we're trying to do is mimic the experiment. In an experimental situation, your rate constants between individual experiments almost never comes out exactly the same. There's always some experimental error in the process of running and making these measurements. Okay? So what they're trying to mimic with this actual data is that you get some fluctuations. When you move into the lab, you will not get your results this accurate. Okay? Which is one of the reasons we have to come up with other ways to kind of average out that error, minimize that effect. Okay? Yes?
So X and Y stays the same for every experiment?
X and Y for each type or each individual experiment will stay the same. So each of these experiments, X and Y stays the same.
So you just find X and Y for like one of the ones that doubles and then the other one is constant?
Yep.
And then you just change the rate and concentrations for every experiment?
To get your rate constant.
And then you get your different constants for every experiment?
Well, are the constants different for each of these experiments?
Well,
So we could pick any one of them, and we'd get the same answer.
okay.
Okay? On an exam, the answer I would give, or the data that I would give, would only give you one option. Okay? I would narrow it down so you don't get multiple different rate constants. If we change the experiment, so now instead of saying this experiment, so this is where it's going to get a little bit confusing. If we change to a different experiment altogether, say in our next step, here we have an entirely new experiment, which means X changes, K changes, Y changes, your rate changes, everything changes. So we have to go through and now resolve for your overall rate expression. Okay? And to solve for that, we have to generate new mini experiments, okay, where we change concentrations and determine the rates for each of those individual experiments. Okay, so X and Y are dependent on the type of reaction or the individual reaction. Once you know what X and Y are for that reaction, it doesn't matter the concentrations. You will get the exact same X and Y values. Does that make sense? Okay. So when we looked at this one, okay, it was a bit obnoxious because I threw this up just to try and solve all the way through. If I asked for the rate at those particular concentrations, okay, the first thing that we would need to do is piece together our rate law expression. I think I got this stepwise. So we've got our example rate law expression. You'll notice that X and Y, in fact, all of the variables, are highlighted in red. We do not know X and Y yet because we haven't solved for them. We don't know K yet because we don't know X and Y. Okay? How do we determine X and Y? We'd have to go back to our data and carefully pick certain experiments and compare those back to the rates. Okay? In the previous case, we looked at where situations doubled. Okay? In this case, we don't have anything doubling. I tried to make it a little bit more difficult without getting ridiculous on it. Okay, we'll look at the ridiculous one in a second, or probably 10 minutes. Okay? So what we would do is, again, build up a similar situation. We're trying to compare individual experiments. That equation that we had drawn up, okay, so this is what we had on that previous page where we compared two experiments to each other. Okay, where did that equation come from? Good job pointing. Okay, you'd think maybe I would give you some hint for it. Okay, it came from realizing that our rate constants for an individual experiment are the same. Okay, so I can say the rate constant for experiment 1 is the same as 2. If I know how to solve for the rate constant for experiment 1, I can compare that to the rate constant for experiment 2. And as we did yesterday, what we can do is then group similar terms. So we can bring the rates to the same side of the equation, and we can bring the concentrations to the same side of the equation. I hope, but I'm not positive, that I set this up the exact same as I did it in class yesterday. Okay? Does it matter where I group the rates? Ultimately not. I could have brought rate 2 to the left side. It would then be in the denominator. That would then have taken these concentrations and brought them to the numerator. Okay? What we end up with is a different number value, but the x and y values still come out the same because we're looking at ultimately at these ratios. Okay? Where we went through and propagated it before is once we had this, in fact, I think I even did it up here, we went through and just plugged numbers in right away. Okay? I'm not a big fan of that technique, but it is perfectly valid. Any ideas why might not be a fan of that method? So there's a potential for wondering where the numbers came from. The other big potential as far as I'm concerned is I'm clumsy with numbers, and I may end up shuffling them around. Numbers are very easy to confuse on where they came from and what you're actually lining them up with. In this format, I can see variables, and I can change those variables very, very consistently. If something's wrong with what I wrote with my variable, I can see that right away. Whereas a number, if I write the wrong number here, the only way I find out is I have to go back and check something else. Okay? So I like leaving things in kind of a general format. Okay? As we did with the last problem, what we do, go through, pick 2 experiments where one of those concentrations stays the same. Why do we do that? Because then that term can drop out. So if we, let's see, did I do the right one? When we compare experiment 2 to 1, the concentration of hydroxide does not change, which means ultimately, regardless of what that y value is, those terms cancel out. The only variable left at this point is that x value. I can then plug in all my numbers and solve for it. Okay? In this case, because most people don't like going through and solving with variables, everybody seems to like using numbers, so I went through and threw in the numbers instead. Here we've got our 0.03 to the y power, 0.03 to the y power. Those values cancel. What we're left with is that x value, and we can go through and solve. This side of the equation gives us 1 over 9. This one gives us 1 over 3. What's the relationship between 1 over 9 to 1 over 3 to the x power? What does x have to be? 2. Let's say you don't know that. Okay? You don't see that right away, particularly if you're using a calculator. Okay? If you go through and punch in a calculator, what you'll see for 1 over 9 is 0.11111, and because it's not exactly 1 over 9, it'll be 0.111134962. 7. Okay? When we go through and do this one, our calculator should give us 0.3333. What's the relationship between 0.1156239 and 0.333? That's a little bit of a harder relationship to see when you write it down. Okay? If you've got it in the fractional form, it's a little bit easier to piece together what happened. Okay? So again, I prefer the fractions in this case as opposed to the decimals. But if you go through and put it in the decimal format, you're not going to see that. How can you solve for x? How can we get that x into a position where we can solve for it? Because ultimately, where does the x need to be? It needs to be in an equals format. Okay? So I have to get the x by itself, but it's an exponent. How do I get it out of the exponent? I think I heard someone say it. We can take the logarithm. This was the part that I couldn't remember. We can take the log of both sides. (1 over 3 to the x power). What does this term equal? We've got an equality here. That exponent can be drawn out to the front. We get x equals the log of 1/3. I can now divide both sides by the log of 1/3, and I'll get a numerical value for x. What's that numerical value happen to come out to? Roughly 2. Well, actually, it comes out to exactly 2 with these numbers. Okay? If we did the decimal value, instead of doing 1 over 9, we'd put in whatever that decimal value was. Okay? What if we'd swapped the equation? Okay? What if instead of doing rate 2 over rate 1, anybody tell what I did here? Rate 1 over rate 2. This one, I think, actually comes out a little bit easier because now you get 9 equals 3 to the x. That's a little bit easier to work with, a little bit more trivial. You don't have to deal with fractions. Okay? What would happen if we tried to solve for x now using the calculator? We get log of 9 divided by log of 3. That's not the same as log of 1/9 divided by log of 1/3, is it? It is. Okay? So the mathematics work out for us regardless of which way we decide to orient the individual reactions, okay, or our rate law expressions. Okay? After all of that work, what did we solve for? X. What did the question want? The rate. Okay? So this is where these questions can get very tedious and very time-consuming when it comes to an exam. You could expect to see maybe one of these types of questions on the exam. I wouldn't ask a whole bunch of them. Why not a whole bunch? It takes so much time, I wouldn't be able to ask any other questions. Okay? So I might ask one question to go all the way back. Can you carefully track all of your answers to get the correct rate and do all of the mathematics to support that? Other questions may be similarly formatted but would ask different things. Maybe instead of asking for the rate, I ask for x. Okay? Or I ask for y, or I ask for k. All of them require varying amounts of work. The x and the y are the easier ones to solve for, so it would take less amount of work. You would expect those to be quicker and easier to deal with. Okay? Does that make sense? Okay. What's the problem with that? If I went through, let's go back. And then this is the data that I give you, and the question I ask is, what is x? There's the problem. What is x? Okay? That question is so open-ended and vague, you have no idea what x means. Okay? So the mathematics work for showing us that dependence. Okay, but we need to come up with a better way to refer to what x actually represents. Okay? And that's where I'd intended to go yesterday and didn't. Okay, so with a general reaction, okay, so in this case we've got 2 reactants, 2 products. It doesn't have to be that. We're just trying to give an example here. Our rate law for that will follow the general form shown here. Okay? We won't see the product show up in that because products don't have an effect on the reaction unless I tell you otherwise. Okay? Or your experiment tells you. The superscripts, in this case I did M and N, I don't know why I did that, have to be solved for experimentally. And this comes back to that whole x and y thing. If I said solve for x, well, what was x here? Who knows? It's yet another variable. Okay? So we need to come up with a better name than just these random variables. That name is the order of the reaction, okay, or the order of that reagent. Okay? So your M or X, N or Y, as we've been seeing, are the order of the reaction with respect to that particular reagent. So in the previous problem, the question that I would ask is, what is the order of the reaction with respect to ClO2? Okay? It involves a lot more words, but now there's no random what is x. I'm very clearly referring to what is the superscript on that term. Does that make sense? Okay, so what does that physically mean towards us? Okay, in the physical world, what is that number? Okay, that's sort of not quite there yet. Our superscripts are ultimately the mathematics. Order is just a way of referring to it in English or chemistry knowledge, if you want to look at it that way. Okay? So it's our way to quickly and easy refer to it. So what do those numbers mean? Okay? If we look at it with respect to an individual reactant or reagent, okay? So in this case, if I said M was 0, okay, that would be the order for that particular reagent. What does that end up meaning to us? Well, as far as the reaction goes, that reagent had no effect on the rate, which means as far as our reaction goes, that reagent is ultimately a bystander. Okay? It has no impact on our rate. We aren't concerned about its concentration whatsoever. it does not affect our overall reaction. What happens if it's a 1? It's now part of the reaction. It has an effect on the reaction. It's now somehow involved in our mechanism or how our reaction occurs. What if it becomes a 2? Okay, now it's become even more involved. If it's a 3, it's become even more involved. How about a 4? We could say it's even more involved. Why is 4 not showing up here? This is not probably the nicest analogy, but it works out. What's the likelihood we can get 4 things or 4 people to all agree on the exact same thing? Okay. How about 5 people or 6 people or 7 people? Okay. As we add more people into the reaction, okay, or more reagents, the likelihood that we can get all of those things to come together at the exact same instant to progress forward to the products becomes exponentially more difficult. So when we're going through and determining the orders, what we've found experimentally is that our most common one ends up being, or probably common 2, I should say, would be the 1 and the 2 being our orders. When we get up to that third order for a reagent, that's really, really high. The likelihood that we can get 3 molecules all together at the exact same instant is pretty minimal. Okay? So we typically don't see orders that go beyond that. Does that make sense? Yes?
Will it always be like just 0, 1, 2, 3, no like decimals or anything?
No. So the easier comparisons are where we have these strict numbers, and those follow neatly into mechanisms, okay, which we'll talk about maybe by the end of today. Okay? And when you move into organic chemistry, that's where you'll see 0, 1s, 2s. Okay? Because they're a lot easier to explain. There isn't anything complicated with how the reaction actually works. It's a fairly simple reaction. You can get decimal values. Okay? Sometimes those decimal values are just experimental error. So if we got an order that was 2.034, more than likely what's the order? 2. Okay? But we could see fractional ones or other values. Okay? Because we're obtaining these numbers from an experiment, and ultimately the experiment was designed by us, and we are fallible as experimentalists, those numbers are very difficult for us to specifically say, is it fully 2 or is it really 2.034? Okay? So those numbers ultimately refer to the mathematics behind it, and we try and associate something to it that we can grab a hold of. And that's where we get to these whole numbers. Okay? As we move into more complicated mechanisms or reactions, you can see feedback loops, products affecting your reaction, different intermediates and things like that that can change these numbers to being non-whole numbers. Okay? These just happen to be the easiest ones to grab a hold of. Does that make sense? Okay. We can then push this excuse me, a little bit further. We can look at reaction orders. Instead of reagent orders or the individual chemicals, we can look at the overall order for the entire reaction. Okay? So we could then, to do this, what we're going to do is sum those exponents. Just add them up. So in this case, m plus n. If m plus n equals 0, I don't think this is quite technically true. I'm not positive on it, so we'll make this extra credit. Find a reaction that has a 0 order reaction that actually occurs. Okay? What does that mean if it's 0 order? There are no reagents involved in that mechanism. How do you have a reaction if there's no reagents? Okay. How do you get a reaction that's independent on anything? So I'm pretty sure that means it's non-existent. Okay? With a reagent, it's possible, because we could say one compound is dependent and one compound's not. But with an overall reaction, pretty sure if you hit that 0, it's not going to run. You won't have a reaction to go. Okay? Once you move up to 1, now instead of referring to it as just importance, we're referring to the number of reagents involved in that reaction, okay, or determining that rate. So instead of calling it, what did I call it, a reaction order of 1, we can simplify that and refer to it as unimolecular. What does uni mean? One, molecular, molecule. If we looked at a rate expression where our overall order was 1, we could go through and cross out B, say N was 0, and M was 1. How many molecules are involved in that rate? One, just A. So there's our unimolecular. When we move to an order of 2, we get bimolecular. So instead of that being a 1, let's make it a 2. How many molecules are now involved in that step? 2. Okay? We're required to use 2 molecules of A to push that forward. So we get the bimolecular term. We could then move to our 3 and get a termolecular term. Again, how likely is that going to be to occur? Fairly unlikely, because the likelihood that we can get 3 molecules all impacting each other at the exact same instant in the exact same conformations to generate products is fairly unlikely. It does happen, it's just not super likely. Okay? Yes?
You said that the sum of the reagent orders are the y and the x value added together, correct?
Yes.
Okay, so we most likely won't find one that has like both x and y as 2 or something like that?
Yeah,
give us
it's
4?
not super likely.
Okay.
That said, there are always exceptions to that, and because that also limits the possibility for questions to ask, I can make up random questions where we get weird results. Okay? As far as the backwards solving of what we had to do on everything else. Does that make sense? Questions about that? Yes?
What does it mean, like in the chemistry, if there's 2 reactants and one's x value is 2 and one's y value is 0? What does that mean? So it's just not doing anything.
So like here? Yeah, so for this reaction, see if I can draw it out. So we get A plus B goes to, just for the sake of it, C. So that could be in our example reaction. What we're saying is that this reaction, B does not play a role in affecting the rate of the reaction. Okay? And what we're going to do is see how we can take the rate expression to decide how this actual reaction occurs. Okay? Which is, I think, one of the more interesting parts of kinetics. We can take this mathematical expression and say, that means that when I draw this reaction out, particularly in this case, let's see, actually let's shift to a new page. Just because I think it's fun. You guys think it's fun too, right? That's where you should say yes, yeah. So if we said that rate was equal to K times, A squared. And this was our overall reaction here. A plus B goes to C. Okay? So what that means is in the course of this reaction, mechanistically, what has to happen is A must react with itself to make something. Okay? Since we're doing variables in this case, we can just make something up. Let's call it, because I haven't used it yet, D. What happens now? Does D show up in my final overall product? Nope. Which means D has to disappear. It has to be a reactant. So at some stage later, D can react with B to now make our C. Now when we go through and look at the overall reaction, how do we do our overall reaction? We just add them together. I see 2 A's involved in this, plus B going to C. Okay. Yes, we see that coefficient show up, and that may depend on the reaction dynamics. Sometimes it translates down, sometimes it doesn't. Is that what you were about to ask?
Well, I was gonna, is it similar to like a limiting reactant?
No. The limiting reactant is something we force on the experiment. Okay. I can make B a limiting reactant by putting it in there in lower concentration than A. Okay. So our rate expression can help us predict how our overall reaction occurs, what steps it individually goes through. Give me back to my slides. There we go. Okay, questions about the order? Yes?
Yeah, so in that example you just had, D would never affect the rate?
I won't say never, but in the case that I drew, yes. It would never affect it, yeah. And we'll look at a case where D can show up, sort of. Okay, when we get into mechanisms, yes? D is not considered a catalyst. To be a catalyst, you must start with it. So D never started the reaction off. D was formed, then it was consumed. So it's not a catalyst, it's an intermediate. Okay? It's a product that was then consumed. That's where we refer to it as an intermediate instead of either a reagent, product, or even catalyst. Okay? Other questions on our orders? You guys are asking all the questions that I like to answer about mechanisms, but we aren't there yet. Other questions? Okay. So when we go back to this question, we can go through and attempt to solve it the rest of the way. We figured out what did I say, X was in that previous example. So ClO2 had what order? 2 or second order. Okay. If we want to find the overall rate, we need to then solve for what Y is. We already addressed that. Yeah, man. So let's go through and actually work through that problem together. Yeah.
Just looking at that graph, once you figured out X, couldn't you say that Y is going to be 2 as well, just because of the ratios?
So that is ultimately what we would do next, and that's what we're going to try and do here. Instead of going through the raw mathematics all the way through, what we'll do is see if we can come up with a comparison.
And would that always work then?
And by looking at the ratios, what are you saying?
For instance, like in experiments, say 2 and 3.
Yep.
That's the same, but then when you go to the reagents, it becomes...
So what you're doing in your head is exactly what I said we did before. What I wanted to show previously was all the mathematics. So if we go through and look at these two, what you're saying is to compare which experiment in the numerator? Experiment 3. So we would say, in drawing mode, we would have 0.09. So experiment 3. Should add the E there, I guess. And we're going to compare that to experiment 2, 0.03. We can then leave this sequence out. Okay? If you want to include it, that's fine. But remember, those numbers are going to cancel each other. Because these are the reagents, these are held to power Y. Did I do Y? Yeah, I did Y. Okay? And we're then going to compare those to what? The rate. Make sure that you put the correct rate on top. We're looking at experiment 3, 0.0828. 2 zeros, thank you. See, I do listen. That was kind of a joke, too. 00276. When we go through and solve this, 0.09 over 0.03 gives us 3 to the y power equals 3. What did you say y was equal to initially? 2. Okay, so, yeah, so, oh, okay, I think I see what you're saying there. Just because you solve for x does not mean y is equal to that.
Well, no, yeah, I was just saying that because on X it looked the same way. If you look at experiments 1 and 2,
Yep.
how it's 3 times.
So a concentration for sure triples, but then when you look at the rate, what happened to your rate? It went up by 9 times, okay, instead of by 3, okay? Sometimes you can see those numbers easily, sometimes you can't. In this case, y ends up having to be 1. Y equals 1. We could now go back to our rate expression, and instead of being y, I'm just going to cross over it. We've got a 1. Okay, so already 2 multiple choice answers have shown up. 2 and 1. Which one do you bubble in? Trick question. It's a very trick question. What was the question to begin with? What's the rate? So 2 and 1 showed up as multiple choice answers. Great, you got a number that's shown up in the multiple choice, that must be right. No. Answer the question. The question asks for the rate. Okay? Which means, which of those two answers do you bubble in? Neither. Okay? It asks for the rate. To solve for the rate, I've got it highlighted in blue so you can kind of see it a little bit better. What do I need to know to solve for the rate? K and those two values. Do we know the rate constant yet? No. So what do we have to do? Well, we have to solve for it. Okay, so to solve for the rate constant, we can set up an equation. We can pick our rate over the concentration of ClO2, what? No, just ClO2 squared, concentration of OH minus to the first power. Which experiment do we pick? Any one of them we want. We'll get the same value for the rate constant. Anybody do that really quickly? Or do you guys trust me on it? Or you already got it?
That is 229.62.
I'm just going to stick with 6. Anybody else calculate it and get the same thing? Okay. So we now know our rate constant. If we want to know the rate, what do we have to do? I know, really tedious, right? We start with our rate equals 229.6. Which concentration do we use? Oh, whoops. I was answering the wrong question too. What concentrations do we use? The ones the question actually asks us to use. Our ClO2 was our 0.1. Remember, it must be squared times the concentration of OH minus. Punch that into the calculator, and we now have our answer. Somebody calculate that too, just for the sake of it. 0.0.
0115.
I got 0.15.
Did you square the 0.1? That's where the difference is, I see.
No, I didn't.
Okay. So you got to make sure you square. Make sure you use those superscripts. That 0.1 doesn't show up very well. Okay. So you said, let me erase those. This brings up an interesting point. You'll notice that when we did the 0.1 here, notice I showed the 0 in front. Why did I show the 0 in front? Why didn't I just do 0.1? Let's go back to what it initially looked like here. What number is that? That looks like a 1. There is a decimal point there. If you look really, really carefully, there is a decimal point. It's not always easy to see that. If we put a 0 in front, now what does it look like? Now it looks like a really weird 1, so now we look a little closer. Oh yeah, there is a decimal point. Okay? That's known as a leading 0. When it comes to lab reports, I'm very picky on that, just so you know. Make sure you include your leading zeros. I'll try and make sure I include them when I go through and solve stuff too. Okay? Yes?
I'm really sorry, I didn't see where the 229.6 came from.
The 229.6, so if we match this back to our rate expression, this was our concentration of OH minus, concentration of the ClO2 squared. This had to be our rate constant. What was our rate constant?
So how did you get it?
We had to get the rate constant by first solving for x and y. Once we had that, when we look at this individual experiment, or sorry, this individual equation, do we know a rate? Do we know a concentration for that rate? Yes. Do we know the concentration of OH minus for that rate? Yes. So the only variable is rate constant. So we can pick any one of those experiments, and we'll get a number that's very, very similar to this, if not exactly the same. Okay? Does that make sense with the rate constant now? Other questions with it? Questions in the back, or you guys think you got it? I'm fine either way. Yes.
Do they always give us, like the ClO2, they always give us those concentrations?
When trying to solve for the rate?
Yeah.
Yes. And by they, it should be me. Yeah. Yes. When trying to solve for K, we can pick any rate. Once we pick that one rate, though, let's say I pick this rate for experiment 1, what concentrations should I use? The ones for experiment 1. Okay? If we go through and pick the concentration the rate for experiment 2, we would go through and use the concentrations for experiment 2. Okay? And that should give us the same value for K. Okay? Why should it give us the same value? K is known as the rate constant. If it's not constant, something's wrong, either with the data that was given to you or with your calculations. On an exam, if you come through and you try to just test that real quickly just to make sure your rate constant came out the same for each experiment, if you're getting drastically different answers, first thing you should do would be, I actually wouldn't recommend checking your work right away.
Check your calculator.
Raise your hand, call my attention to it. I'll take a look at it to see if there's a mistake. What should you do while waiting to find out if there's a mistake? Go to the next problem. Okay? If there's a mistake in it, and you spend all of your time trying to find what your mistake is, and it's my mistake, you just wasted 20 minutes of the exam time on a problem that I'm going to throw out. Okay? So if you don't get something matching up correctly, just raise your hand and ask. Okay? I usually try and go through and do the exam at least 3 or 4 times on my own with all of the work, and trying to go through and find out how I got wrong answers as well. So I end up having to do the exam, like I said, at least 3 or 4 times for the correct answers, and then another 2 or 3 times with the wrong answers to make sure I know where they're coming from. So in most cases, I've caught those mistakes. It shouldn't be an issue. Okay? But if it does show up, don't waste your time on it. Raise your hand, ask. Maybe I've done it multiple times. It's one that I remember being tricky. I'll go back and either say, no, I'm positive that's good, in which case now you can check your work, or you can move on to the next problem and wait for me to figure it out. Okay, does that make sense? Okay, when it comes to exams, it's something that I'm really, really big on. I do want you to ask questions during the exam. If you don't understand what's being asked of you, the test question isn't particularly helpful. Okay? I try to mimic the exam questions so that they match the homework and what we've talked about in lecture, so it shouldn't be too much of a surprise on the formatting of the questions. You've got practice exams to look at, so like I said, it should run fairly smoothly. Okay? Questions about this? Okay. How can I make it more difficult? Because of course we always want to do that, right? Okay. Uh-oh. So, how can I make it incredibly more difficult? What's the rate law for the above reactions? If I ask for the rate law, okay, I'm asking for specifics. What are the orders with respect to all the reagents, and what are the rate constant, or what's the rate constant for that reaction? So you need to go through and solve for all of those things. Okay? Why is this problem drastically more difficult than any of the others? If we go through and look at the concentration of NO, okay, we could compare experiment 1 to 3 because bromine stays constant. So we could figure out the order for NO. What about the order for bromine? None of those stay constant. How would we solve? Deal with it. Let's see, because I'm pretty sure I got it back here. Guess C. Maybe. Remember our mathematics behind this. This was our expression, and we went through and simplified this. Okay? If I know what x is, okay, does it matter that these two terms cancel each other out? No. So that problem becomes more difficult because you can't cancel a term out. You must include it in your calculation. But at that point when you include it, you know what the x value is. Okay? So that information is solvable. It just requires an extra step. It requires understanding that this is the relationship that you're using. This is where all of your calculations are based from. When we look for the double or triple or any of those multiples, when we're looking at the raw data, that's ultimately what we're doing in our head. And we try to pick experiments where that equation simplifies and becomes easier to understand. Okay? I'm not going to go through and solve that problem beginning to end. But I will tell you at the very end of the slides, okay, so it's something like 70, 75, I do have all of those answers posted, okay, or the full explanation all the way through it. Okay? So you can go through, check your work with that. To me, this is kind of an A letter grade type question. It tests the math extensively. It tests the chemistry as well. Okay? So if you're one of those students that's really pushing for an A, you should be able to do this problem. Okay? If you're someone just trying to figure out if you understand it, you should be able to do this problem as well. That should be a good test for how well do you understand how to do these calculations. Okay? Make sense? Okay. So we've now looked at concentration. We looked at the nature of the react. Sorry, was that a question?
Yeah. So is there any difference between that question and what we just did?
The only difference here.
Except for we're solving for the law and not the rate.
Yeah. So we'd be solving for the rate law, not an individual new rate. So what we would need to solve for is this expression. Rate equals K times, what we got? NO. BR2, right? And then this has X and Y. Sorry, that got a bit crowded there. That expression is what you would need to tell me.
But are we doing the same thing as we just did?
It's the same steps. You don't have to take it quite as far. With the last problem, I asked for a very particular rate. With this one, you just need the rate expression. This is what your answer would look like. Be in that kind of format. You'd have to know what X, Y, and K are. Those numbers would show up in your expression. Does that make sense? Okay. So this is solving this problem is one step back from solving the other problem.
Just solving for X and Y.
You still have to solve for X and Y and K, yes. Okay, other questions on that? Okay. So we've now looked at the effects of concentration. We've seen the nature of the reactant. We kind of looked at mechanism a little bit, and that's probably something I'm going to post over the weekend. Temperature we're going to look at probably also over the weekend as well. And before we even get into catalyst, there's one extra thing that doesn't show up on there. What issue do I kind of have with this? What happened to our time? Okay. At no point in our rate law expressions do we see an actual symbol for time. Okay. Why did time disappear from our experiment when time is what's determining our rate? Okay. So time should have some effect on this. And it can be incredibly important to include. Okay, why? When you get into lab, what's your primary focus in lab? Be honest. Getting out of lab. Okay? Don't worry, all chemists have the same opinion. Okay? So if I'm going to set up an individual experiment, I want to have an idea of how long it's going to take for that experiment to occur. Because if I know it's going to happen in 20 seconds, I'll stick around for it. If it's going to take 5 hours, I'll go out, have lunch, go to the bar, relax, come back to the lab, see it's not done, make sure nothing exploded, then go back out. Okay? So having an idea of the time it takes for a reaction is really helpful as far as personal lives when it comes to chemistry. Okay? So we need to come up with some way to get time back into this. Okay? As a warning, for those of you that haven't had calculus, this is where calculus rears its head. Okay? It's not that ugly, but it's not pretty. Okay? Time was involved in our expression. Time showed up in how we determined our rate. Okay? And we could look at large changes in it. When we looked at our individual rates, we actually said we took an infinitely small approximation. So instead of looking at a delta t, where we're looking at large differences, we looked at a very small difference. Mathematically, when we go through and do that, whoops, I thought that was stepwise. Mathematically, what we're saying is we're going to look at a very, very small difference. Instead, what we do instead of a delta is a lowercase d. Okay? For the sake of argument, let's just call that d our derivative. Okay? What we're looking at is the derivative of that line. What we can now do is take our equation and start to group like terms. I don't see t anywhere over here, okay? But I also have another derivative function here. So I want to get these two away from each other onto opposite sides. So I'll shuttle the delta t, or sorry, the dt to the other side. Concentration of A, so our derivative of A. Okay? I've got a concentration A over here. I want to again group those like terms. Okay? K, what is K? A constant. Okay? So a constant doesn't have any dependence on time or our concentration. Okay? For the sake of argument, we decided to keep our rate constant with our dt. Okay? To go ahead and eliminate our, not called a derivative anymore. What's calculus people? What do you refer to the d as? Nobody? Okay, well, we'll call it the derivative since no one's going to argue with me. Okay? We can then go through and take the integral of both sides, and we're going to integrate that from time 0 to some unknown time, and we'll integrate the other side from concentration 0 to some concentration at that final time. So we're integrating our equation over the same area, okay, our same distances. When we go through and run that integral, what we end up finding out is that our rate constant disappears or shuttles out to the outside, and what we get is time minus time 0. Okay? That's what ends up translating from this equation. Okay? When we go over and do it on the other side, this one gets even meaner. Okay? To do the integral of 1 over the concentration of A, it ends up equaling the natural log. So when we go through and solve that, we get the natural or the negative natural log of the concentration of A at time plus the natural log of concentration at time 0. Okay? Now what we can do is kind of rearrange that and solve and simplify. What's the simplification that I made? What's time 0? 0. It's ultimately the only simplification I made. So this term drops out. I get kt. I can then try and shuttle terms around each other in this particular fashion. Any idea why I picked this particular arrangement? What's that? What I've got in this format is y equals mx plus b. What is that equation? Straight line. So by going through and bringing time back into it, I could now potentially plot some data, and I could see a straight line. From that straight line, I can pull some information off of it. What is m? What is the slope of that line? Negative k. So with that data, instead of going through and comparing all the experiments, I could go through and solve for the rate constant without having to calculate all those other things. So a plot or a graph can help me solve this without having to evaluate each of those individual experiments and do all that funky algebra. So instead of algebra, we do calculus. Probably algebra is easier. Okay? Yes?
So the little stool showing the relationship between the subscript and the superscript attached to it?
Because I haven't taken calculus in a really long time, the squiggle is saying that you're measuring the area of that data from those 2 points, from that data set.
What did you say the ln stands for?
Natural log.
Natural.
Yeah. It's something just in your calculator. You can just punch that in. It should just be an ln value. Okay? this equation becomes helpful, and that's ultimately the boxed in one is the one that you would need to know. Okay? When is that equation valid? For a first order reaction only, which means what's the exponent or our overall order for the reaction? 1. So it also gives us something or some information about the order for our reaction. Okay? We have to be a little bit careful. You'll notice how many reagents are showing up in my expression. Only 1. Okay? When we go through and do our integrals and get to our time-dependent rate laws, we're only going to evaluate 1 reagent at an individual time. Okay? So these expressions or these reactions become a little bit more simple, and that reaction, drawn awfully terribly, is just A going to our products. Okay? What happens if we change the reaction? Let's say if we look at a 0 order calculation. Okay? For a 0 order reaction, rate would equal what? K. Our concentration of A is not valid to our rate, so it doesn't show up on our rate expression. Okay? So we could go through and try and solve this. Again, we know our rate is equal to, because we're doing a disappearance, we've got the negative delta A over delta T. We could simplify those deltas into our lowercase d's, and we could go through and again do the integral just like we did before, and what we end up solving at the end is this expression. Okay? For a 0 order reaction. Do you want me to do all the integrals? I like the head shaking. Thank you. I don't want to do them either. Okay? What you're ultimately responsible for is this equation. When is this equation valid? Only for a 0 order reaction. Okay? Could we rearrange that equation a little bit? What if we changed it ever so slightly into concentration of A at time equals to negative KT concentration A times 0? What's that?
Substituted?
It's not a substitution. In this case, all we did was just swap those terms. We added A sub 0 to both sides. Why is this format a little bit more interesting? Equation of a straight line again. So we could go through and plot our data, determine this straight line. Okay? We can go through and do it for a second order reaction. Now it gets a little bit more complicated. Our rate equaling to K with our concentration of our reagent squared, because it's a second order reaction. Again, we go through to do the same kind of comparison. We know our rate is equal to the change of A versus the change of time. And we can go through again all that fancy calculus. And we end up with our final answer here. We could again go through and rearrange this into the format of a straight line, or the equation of a straight line. And we then again have another way to look at our data graphically and allow us to determine the order and our rate constant. Yes?
Will these equations be given to us on an exam?
It's a good question. I've been waiting for someone to ask. Yes. If you take a look at just, I think, the files, I think is where I put it. There should be a file name that might be E3 equations, something like that. That list of equations will be given to you on every single exam. Any ideas why I give you all the equations? No, I'm not particularly nice. What's that?
When you don't require us to remember them, or that.
So why would I not require you to remember them?
Using the real world.
In the real world, you can look them up at any time. There's yet another reason, because you'll still find tons of professors make you memorize them. How good's my memory? It's pretty awful. And if I can't remember the equations, it's not really fair of me to expect you to remember the equations as well. Okay? So it kind of reflects the real world a little bit better, and it also makes me feel better because I'm not punishing you, making you do something that I wouldn't do. Okay? So you will be given these equations. You will not be told what they mean. So you'll see this equation. Let me move to the next slide, actually. You'll see these equations shown But the information that you're going to get, or the 0 first, second order things, aren't going to show up. The only thing I'm going to give you is the equation. You need to know when to use the equation, which equation to use. Okay? I know, small thing, okay? But you're still responsible for that. Okay? Does that make sense? Okay, so if we look at our time relationships, we end up with this, summarizing all of those individual orders. These are known as the time-dependent rate expressions. Why would we call them that? They're time-dependent rate expressions. Okay. Sometimes we use English appropriately. This happens to be one of them. All right? So the thing that's helpful here is now you can solve, if you've got it plotted, you can solve for individual rate constants and also the order. If you look at individual graphs, which we'll look at in a second, you can also go through and solve for the time. If you know how much stuff you started with and you know what your end goal is going to be, how much concentration you want to end with, you can now solve for the time that it's going to take to do that relationship or do that transition. Okay? And because I don't think it's on the next one. Okay, so while that's all nice and fun, we can rearrange the terms, which we already talked about, into this format. What's special about this format? These are all the equation of a straight line. Okay? That can be helpful because if we run an experiment, there's a couple things that we're going to record right away. We'll have concentration and we'll have time. Okay? Previously, what did we do with the concentration and time? We went through and calculated a rate. Then we went through and compared experiments to determine what orders of each of the reagents there were in there and all that fun stuff, to put it politely. Okay? That's an awful lot of mathematics to figure out what the order is and what the rate constant is. Instead of doing all of that, I can take that data, particularly in a graphing program, and tweak it. So the first thing I could do is plot the concentration of my reagent, okay, just my concentration, versus time. What happens if I see a straight line? What's that?
You have a constant.
I could determine the rate constant, yes. More importantly, what's the order with respect to that reagent? 0 order. So when I go through and plot that data, which in Excel or other graphing programs can take a matter of just a couple minutes, I can very quickly determine the order of the reaction. Okay? So with the computer tools, we can get to answers much quicker than we can looking at all of the data and doing all those comparisons in the algebra. Does that make sense? Okay, what happens then if I go through and I want to figure out if it's first order? What would I have to plot now? I'm hearing it. I would plot the natural log of my concentration versus time. If I get a straight line then, what does that mean? It's first order with respect to that reagent. I can use the slope of that line to determine what our rate constant is. What would I do in this case? If I think it's second order, what would I plot? The inverse, if we want to get fancy with it, or just divide 1 over our concentration versus time. Okay? And I could then look again for a straight line. Okay, so ultimately what this, oh man, that wasn't supposed to happen. What we're looking at is something along these lines. Okay, I know those axes are a little bit small. And we'll end with this discussion. Okay? So if I took the data from the very first experiment, which is what I think I did, okay, our bromine thing from way back when, so long ago on Tuesday, okay, and I plot the concentration of bromine versus time. In that plot, what am I assuming? I'm assuming it's 0 order. So I will try and fit a straight line on it. So that straight line is now the black. Okay, so I can tell Excel or my graphing program to fit the data. Does it look like the straight line matches my data? No. What does that mean? It's not 0 order. So we move to the next graph. And in this next graph, I know it's difficult to see. What am I plotting on the y-axis? The natural log of the concentration versus time. I then tell my program to fit the data again with a straight line. What do I see? Straight line fits directly over the top. What does that mean about the order with respect to that reaction? It's first order. Did we solve it last time? Yeah, we did. What was the order with respect to that bromine reaction? It was first order. And we discovered that after a lot more effort than just plotting these. Okay? We could go through and attempt it with the second order one as well and try and run our calculations. This time, 1 over our concentration versus time. Okay? So given these sets or this set of data, I know that it's a first order reaction. I can take it a step further. You'll see very, very small up there. Using Excel, I can ask Excel to not only draw the straight line on it, but to tell me what the equation of that straight line is. I now have that equation. What can I use with that equation? I can find the slope. The slope in this case happens to be negative 0.0035. What is the rate constant? Careful. Go back to your equation, which in theory you have written down. The slope in our equation was equal to negative k. What's our rate constant? Positive 0.0035. Okay? Given this set of data, which one corresponds to 0, first, second order? Nope. We'll look to the y-axis. We're looking at 1 over the concentration, which matches which expression? Second order. Move to the next one. We're looking at, I can't see that. That is concentration. We're looking at 0th. Let's do 0th. Why not? 0th order. What do you think that last one is? Third order. No, I'm lying. First order. Okay? Kind of makes sense? So the idea is that we can quickly look at that data and try and interpret it as quickly and swiftly as possible. Okay? That's our goal behind this. Okay? I know I'm running out of time here. In fact, I think I'm pretty much out of time. And this froze too. The last thing that we'll talk about in a lecture that I'm going to post to YouTube, that I'm going to expect you to watch before Monday, is looking at half-lives. And I think I'm going to push through the rest of the kinetics chapter as well. Okay? The reason I'm going to post it and expect you to watch it over the weekend is not because I'm mean and evil, but what we're going to do instead on Monday is try and work problems. Your homework is officially due on Monday, so what we'll do is spend roughly half the time, half of Monday's lecture, working just homework problems, trying to make sure you get more comfortable with the material and being able to solve these things so you can get through the homework more efficiently. Okay? That lecture will get posted, I'm hoping, by the end of today. Kind of depends on what happens after this afternoon.